sometimes if you have a hungry eigenvalue, you have to assign then normally. You don't assign all of them. You assign only some eigenvalue which are really important to your disturbances. But you don't have to assign all eigenvalues. If I have a hungry eigenvalue, you may assign only a few of them and keep all the eigenvalues, other open eigenvalues the same thing, because they will not really affect your performance. Or you might think, you might say, okay, I don't want to change all the frequencies, like what I did. I just add some damping for eigenvalues. So again, normally we don't change our frequencies unless we really need it. We just add damping. And you can add them in all the same percentage damping for all eigenvalues, then that's become easy, right? So to assign eigenvalue, there are some something you have to think about. If you want to simplify your assignment, then you can assign all the same percentage, 10% for all the eigenvalues. And that makes your problem easy. And we can also assign the desired eigenvectors just open to eigenvectors. Then you don't have to worry about eigenvectors, right? And also you can also assume that my desire gain related matrix, just like this desire, this part. The desire here, this part. We can make the desire one, and of course we want to make as small as possible, and 0 is the smallest. So we say desire 0. So you can do that. But for single input and single output, you don't have freedoms. So it doesn't matter what kind of design you have, you can get it. So you really have no freedom for single. So there's no freedom. There's no freedom. No freedom for single input. For single input problem. For single input system. That means it doesn't matter, no matter what design you have. What desire, I came back to see that. You can get it. Yes or no, oh, okay. No matter what the desire, again, vectors, we can not reach it. So, the freedoms started when you have multiple inputs. So whenever you have multiple inputs, then you have some freedoms. If you have more inputs, like I have a 3 input or 4 input, then you got more freedoms. Yeah, like that. But for this case, for our system like this, the system we have, the maximum input we got is 2. So that's all. You can have 3. Because this is a mechanical system, and you got that's all you get. Okay, I think that these chapters we're learning enough in these chapters. Now we use the state feedback, the full state feedback to relocate the system eigenvalues. For the first day feedback, we apply SVD to generate the space within the closed-loop eigenvectors shown inside. That's we hope that the closed eigenvector will, well, that's not we hope. That's the space that we know the closed eigenvectors should be in that space, that what eigenvector would be the best for us, and we have to show you a way to get that. That means you can solve its constant matrix C, constant vector C, such that you choose the eigenvectors as the orthogonal as possible. We minimize the state feedback gain by choosing a desired eigenvector as orthogonal as possible. We assume all the state variables are available. All state variables are available. But if they are not, then you will have to use the observer, the state estimator, to estimate your state. This technique is applicable to continuous time and discrete time model, exact the same process for the first order and second order models. So your homework, I give you the homework is discrete time. My example here is continuous time, but exact the same process you want to do. So you just follow the example I give to you today for continuous time. You will be able to solve your homework number 8 and part B. Exact the same process. Okay? And that's just for your exercise. Alright, I think I will end it today to this time. Those class. That's all I got for pole placement technique. Again, I can talk more. There's many other methods to do this, to do pole placement. But I'll just show you, so far, I think this is the most useful pole placement technique you can have. Most of pole placement technique in our textbook, they only talk about single input case. But here you can have all kind of multiple input to design your closed-loop eigenvalues, and that's the advantage of this technique, and also very stable technique like that. Right? Do you have any questions? On both sides. Have any questions? How about here? Do you have any questions? If you don't have any questions in remote site, then you feel free to leave the classes.
Check on my the name of the file, the work file. You sure?
You see your name is homework 4. Your homework 5.
Really? When did you send it?
Sunday.
Really? Okay.
You upload in May 2 or May.
Yeah, on Thursday. Okay.
Okay.
Because I did everything in MATLAB, so I did random sign-on, and maybe I uploaded one more.
Okay.
Okay,
Okay.